Hello, my name is Jeff Hazboun. I am a postdoc at University of Texas Rio Grande Valley. I'm a Physics Frontier Center postdoc funded through NANOGrav, and I'm the chair of the Pulsar Signal Simulator Working Group. And I wanted to tell you a little bit about what the working group does, what our aims for the simulator are, and how that fits into the bigger picture of NANOGrav. So the goal of the simulator working group is to develop an end-to-end simulation that accounts for propagation effects and instrumental effects on the pulses as we get them and need to analyze them. So the simulator is Python-based. It lives on a GitHub repo online, so we can access the code from this repository. This helps us with version control and allows many people to work on one piece of code at a time. This is an attempt to do it how the professionals do it. We use IPython notebooks or Jupyter notebooks to develop the code and to use the code as well, and there'll be an example notebook on the notebook server as well, so you can take a look at that. One of our main goals is to sort of look at the statistical covariances between the interstellar medium and the intrinsic pulsar effects and trying to understand all of the noise sources in our signal. Since we can't go to the other end of our gravitational wave detector, it behooves us to try and simulate all of the problems that we could have, all of those noise effects, so we can understand them better. We also, as a goal, want to be able to use the simulator to test pulsar search algorithms. So we have all of this data that we take in searches, and we want to be able to get those algorithms better and better, and so eventually we hope to have the simulator working towards that goal. Another thing that simulator is really good for is as a teaching tool. So hopefully you'll see if you jump on that notebook that you sort of can play around with the signals really easily and tell different things about them without all the noise sources added up on top of each other. So you can add them one piece at a time and add the propagation effects one piece at a time. Another use that this for the simulator eventually will be to use it to help us develop ideas for new observatories and new telescopes. So this is really a slide about pulsar timing, but the idea that I wanted to point out from this is that we have a lot of processing that happens, right? And there's actually a lot that lives between the pulsar and the telescope. So there's the timing models and the ephemeris models and things like that, but those pulses also have to go through the interstellar medium, and that is a source of noise, right? So we can't just look at the residuals that are on the bottom here for 1713 and see a wave, see a gravitational wave pop out. So we have to do some serious statistical analysis, and so we have to understand all of our noise sources really well. We have lots of noise sources, and we know some characteristics of all of them, and so we can kind of use them to decide how to do our statistics better. And I'll note that really the gravitational wave background, the stochastic background, and we call it stochastic because stochastic means random, because it's many binaries the waves from many binaries coming at us from many different directions. It really manifests itself in the data statistically as noise. And so we need to understand that aspect of the signal plus all of the other aspects of the signal as well. And how they're correlated. Are they correlated in space? If they have a correlation, what kind of correlation is that? Are they achromatic or not? So this just means what's the frequency dependence of the noise? If I look in the Fourier domain, is it random or is it not random? And how it's dependent on frequency. So we have to establish these tools to tell the different noise sources. And the simulator is really an attempt to model these sources so we can understand things better. These are from work by Michael Lamb. I think this may be his dissertation, actually. And you can think of the sort of two classes, broad classes of noise. And one of them is white noise. So white noise just is like the noise on a television screen from an antenna, if you've ever seen that. But the white just refers to partly its statistical properties. It's very random. The distribution is a Gaussian distribution, which if you know any distributions, you probably know the Gaussian distribution. Normal distribution is the same name. And that comes from lots of things. The radiometer noise, which is actually a byproduct of the telescope. The pulse jitter, which is intrinsic to the way that the pulses are emitted from the pulsar itself. This is the diffractive interstellar scintillation. So as the pulses travel through the ISM, they get refracted and scattered, and those things add to the noise. And then there's these red noise processes, and red noise just means that it's a low frequency. So you see this upper curve here. It doesn't look like white noise. It doesn't look super random. It's correlated in time. And so the idea is if I took the Fourier transform of this, then there would be lots of things in the lower frequency bins of this type of noise. And there are many things that manifest themselves as red noise. Spin noise, which is manifest to the pulsar. DM variations, so changes in the dispersion measure that we see on our line of sight, that can manifest itself. And these are these f's to the -5th, the f to the -8/3. Those are sort of characteristic dependencies of the frequency in the Fourier domain. And the gravitational wave stochastic background, it manifests itself as a red process. And again, red just means that if I look at the Fourier domain, I don't have frequencies all over the place. There's more frequencies at low frequencies. There's more power in low frequencies than there is in higher frequencies. So we need to understand these things. And more importantly, or also importantly for the simulator, is that we want to understand how they all work together. So we want to add all these pieces together, and as we change little knobs, we want to understand how those things change. This is a picture of scintillation, and the idea here is that the light comes from the pulsar, and these wave fronts are spreading out as they come from the pulsar. It hits a screen, and you note the screen is supposed to be the ISM here. It really has the same distribution as clouds. It's called a Kolmogorov medium, but basically it just means it's a turbulent medium that looks a lot like clouds or atmosphere. In this case, it's the interstellar medium. Those rays get bounced around. Sometimes, a lot of the time, right, the rays get bounced around and don't make it to our telescope, but some do. And some travel very different paths to get there. So some go very short paths, some go very long paths, and at different frequencies, this actually manifests itself in a couple of different ways. But on the right here, what I've shown is how scintillation happens, which is that at different frequencies, since the lights travel different paths, it can interfere with itself coherently, or it can interfere with itself destructively or constructively. And so you get bright spots where it interferes constructively and dark spots where it interferes destructively. And on average, it ends up being an intensity of 1, the way it works. So this affects our signal. This adds noise to our signal because this is the intensity from the pulsar. It has nothing to do with the intrinsics of the pulsar, just how the signal is moving through the interstellar medium. So that's something that we have coded into the simulator, and there's lots of little projects that we need to do to kind of make this more realistic, but the simplest version is in there. Another thing that we've got coded in is dispersion effects, and point out one of my REU students from the summer, Amelia Henkel from University of Connecticut, worked on this project, and she basically was looking at our voltage versus time signal, which is often what people refer to as the baseband signal, which is just the voltages from the telescope directly. And this black pulse is the pulse as it would be emitted from the pulsar. And this purple pulse is what happens when it gets to us. Now, the dispersion measure here isn't very strong, and it's just so that we can show you some of these neat effects. So obviously the pulse itself is delayed, right? So this is sort of the infinite frequency pulse, how it would get to us if there wasn't any dispersion in the way, if there's no ISM in the way. As it travels, the different frequencies get slowed down by different amounts. And so many of the high frequencies kind of come as this block, and they're slowed down to some amount. But then the lower frequencies, which you can see these sort of low frequency elements, actually arrive later because they get slowed down more. And there's some signal processing tricks that you can do for this. A lot of this is in the Pulsar Observing Handbook. You can find all of these things, how to do this, and so we coded this into the simulator, one of our summer projects. We also can look at filter bank data, and this is sort of the more standard picture of that. This is one pulse at a time. One of these lines is one pulse at a time, and the high frequencies arrive before the lower frequencies do, and there's this 1/f² dependence that we see. Another thing that we've coded in, this was another REU of mine from the summer, Cassidy Wagner from University of Oklahoma. She coded in a way of simulating these scattering effects, right? So there's this thing called scatter broadening, and what it does is, because, if I go back 2 slides here, because some light has taken longer to pass, even on the scale of the width of the pulse itself, you can get these scatter tails where what happens in the tails is that those are the parts of the pulse that have traveled much further than the original pulses. And so you get it, not only do you lose sort of these small little bump effects, but you get this long tail, and it's also frequency dependent. It's dependent on 1/4 squared. So this is a different effect that was coded in a different way. Here she did some convolving, which is another signal processing tool that we have. Sort of very nice encompassed little project, right? You take a signal, you do a couple things to it, write a couple functions, and then you fit it into the simulator where it goes and do some testing on it. So that's the kind of thing that we do with the simulator. It's got this long chain, a nice skeleton of stuff, and we build little pieces on it to make it more and more realistic as we go. One of the more fun things that we've done recently is sonifying pulsars. So if we interpret the radio waves emitted by pulsars as sound, we can play them as audio files. So this is not, these are radio waves, so they're light, they're not audio, but we can pretend that they're audio and play them. And this will allow me to go to a web page here. So this is my web page at UTRGV, and we can play some of these sounds. Hopefully this will play. So that's what 1713 sounds like in real time. It kind of sounds like an angry little bee in your ear. If you can't hear this, you can get to these sounds. You can make these sounds in the notebook itself, or I can provide the website, which is faculty.utrgv.edu/Jeffrey.Hazboun, and that will get you to these slides. So yeah, so that is when it's really fast. I can make it a lot slower. So what I've done here is I've made the hertz. This should be hertz, not megahertz. To the pulses that are 218 hertz from 1713 to beats per minute. So 218 beats per minute. So it's slowed down by 60 times. You can hear the individual pulses here. Now these are the pulses as they leave the pulsar, and you can also disperse them and see what they sound like. And if we do that, this one takes a little while to load. Let's see. If we disperse them, they actually sound a little bit different. And this will sound a little bit like a sci-fi sound effect that you've probably heard in the past. And this is actually how they make that sound effect, is by dispersing the sound. So that's what 1713 would sound like as it reaches us if we slowed it down by a bunch. So, okay, so just to finish up, one last thing again is that we are trying to work on these making realistic signals so that we can put them into real data, so to help us with search algorithms, to look at the data that's being kept from all of these different searching surveys that we're doing. So in summary here, the Pulsar Signal Simulator Working Group is actively trying to understand our detector through modeling. It's a great way to learn more about pulsar signals and the processing we do to get to our time of arrivals that we need for our gravitational wave detection algorithms. It's a great way to learn some Python coding, and it has many small-scale projects for students to work on if you're interested.